So now that we have transformed our features and targets into a suitable form to be an input to a machine learning model, we are now ready for the next step, that is model training and evaluation. So model training or model building is a process that involves fitting a machine learning model to the training data. That means to train a machine learning model using the training data. In this stage, the model tries to learn the patterns and relationships between the training set, that is, between the features of the training set and its corresponding targets. And thereby it enables the model to make predictions or classifications on new and unseen data. Please note that at the time of training, the model tries to learn the mapping between the trained features and the corresponding targets, and by making use of that mapping, it tries to classify a new and unseen data point. And once the model has been trained, then comes the next stage of model evaluation. So, in this stage, we try to evaluate the performance of a trained model, and we try to find out how well the model generalizes on a new and unseen data. That is, we are trying to assess the ability of the model to make accurate predictions on new and unseen data based on its training. We cannot solely rely on a trained model which has not been evaluated. That is because sometimes the models does not learn what they are intended to learn and they don't perform as they are expected to perform. That is why we should always have a check, and that is why we have to implement model evaluation just to check whether the model that we have trained is behaving in the expected manners or not. So, in this section, we will walk you through the code that trains a decision tree classifier and evaluates its performance on the iris dataset. So let's come straight to the code. We begin by initializing a decision tree classifier with a random state for reproducibility and then train it on our training data, as you can see here in these two lines of code. Here in the first line of code, we are initializing an object of the decision tree classifier class which is being named as dt, and here in this class we are passing in the parameter random state which has been set to a value of 42. This is meant to indicate reproducibility of the results. Once the object has been initiated, by using this object we call in the fit function to which we pass the features and the targets from the training set so that the model can be trained on it. And once this line of code is run, then we say that a decision tree model has been trained on the training data set. Now that our model has been trained, we have to evaluate its performance as well, and for that we'll first have to make some predictions. And for this we are going to use the test set, particularly the features from the test set. So here in this line of code, what we are trying to do is, by making use of the features from the test set, we are trying to predict the target for this set, that is stored in the variable called ypred. So ypred is nothing but an estimate of the y-test values which the model has predicted based on its learning in the training stage. So now that we have an estimate of the target values that we already have, we can compare these two values in order to check how much the estimated values or the ypred values differ from the original values, that is the y-test values. So what we want is, if the model is good, the difference between the ypred and y-test values would be very less. And if the model did not perform good, then the difference would be very far apart. To calculate these sorts of differences, we are going to make use of some functions that we have already imported in the first step. Firstly, you can see that we are trying to calculate the accuracy by making use of the accuracy score function, and to this function we first pass in the original y values, that is the y test values, and then we pass in the estimated y values, that is the y pred values. Please note that the order matters, so original values come first and then the estimated values. Accuracy measures the overall correctness of our model's predictions, and it tells us the percentage of correctly classified instances. In the next line of code here, you can see that we are calculating the precision by making use of the precision score function, and to this function also we are passing the original and estimated y values from the test set. But the one thing that is different here in this case is this parameter called average. Here we are setting it to weighted because in this particular project our target variable is not binary. If it was not binary, then we won't be needing to set this parameter, but in this particular project our target variable is having 3 values, that is the 3 species of the iris flower, and so in order to account for the 3 species we have to set this parameter, and this ensures that all the 3 values are being averaged to calculate the precision. Please note that precision assesses how many of the positive predictions our model made were actually correct. Next, in a similar way, we are calculating the recall score as well by making use of the recall function and setting the average parameter as weighted. And recall is also known as sensitivity or true positive rate. And this evaluates how many of the actual positive instances our model correctly predicted. Now, in the next few lines of code, we are just printing all these values and we are rounding them off to 4 decimal places. And you can see here that the accuracy, precision and recall in this case comes out to be 100%. But this is a very unrealistic result. That is because in real world scenarios, nothing is so ideal that will result in accuracy of 100% and precision and recall as well. But since this data set is very small and there is no class imbalance, and basically this data set is a hello world data set, and that is why it is not having too many shortcomings in it, and therefore our model was able to generalize well over it. But let us see another picture, that is of confusion matrix. Here we are calculating the confusion matrix by making use of the confusion matrix function and passing in the original and predicted value of the targets from the training set, and you can see here that this is the confusion matrix. So a confusion matrix is a table that is often used to evaluate the performance of a classification algorithm. To understand it a bit better, we will look at this figure along with this matrix. So here you can see that the rows corresponds to the original values or the actual values, and the columns correspond to the predicted values. In this case here, the values are not being represented by their name, they are representing by the number of their rows and columns, that is 0, 1, 2, and again for columns 0, 1 and 2. So column 0 represents the Setosa class that has been earlier set as 0 in here, as you can see, and then 1 is corresponding to the iris versicolor and 2 is corresponding to iris virginica. So these are the species that we will be dealing with in here. So the first row is for Setosa and first column is also for the predicted value of Setosa. Okay. So this is how we read a confusion matrix. The actual classes are represented by the row and the predicted values are being represented by the class. So here if you would look at this figure, you would come to know that in the test set for this particular image, there were 16 data points for Setosa and 15 data points for versicolor and 14 data points for virginica in the test set. And once the test set was passed into the model for prediction, out of total 16 of Setosa, only 14 were predicted as Setosa correctly and the rest 2 were misclassified, out of which one was considered to be versicolor by the model and the other was considered to be virginica. So that is how we can read a confusion matrix, and this gives in us a glimpse of the bias of the model. Okay, so you can see that again in versicolor, out of the 15 values, 11 were correctly classified as versicolor, but 3 were classified as virginica and 1 was classified as Setosa. So by this you can interpret that the model is being confused between versicolor and virginica. Okay, and somewhat between Setosa and versicolor as well, but there is a very less difference between versicolor and virginica, and we also saw that in our exploratory data analysis section as well, that versicolor and virginica had quite a lot of regions that were overlapping. So that is being reflected in here. So this is how we can evaluate the performance of a model by making use of the confusion matrix. These values 14, 11 and 10, in which the classes are correctly predicted, are called true positive values. That is, these are cases where the model correctly predicted the positive class, where Setosa is being correctly predicted as Setosa and versicolor is being correctly predicted as versicolor. Now after that, there are true negatives and true positives. So this is our confusion matrix in this case, and the rows correspond to the original values and the columns correspond to the predicted values. Now let us also check out the count for each of the class in here. So here you can see that for the Iris setosa species, we had 10 data points in our test set for the target values, and for versicolor we had 9 data points, and for virginica we had 11 data points, and all of them are being correctly classified, as our accuracy is also 100%, so the model is not making any kind of mistakes in here. So that is how you are going to read this confusion matrix. So all in all, it seems that there is no bias in our model, and we can move on to the next step, that is printing the decision tree. Let us first discuss the code, and then we will try to understand how the decision tree algorithm works. Here please note that we have also imported the tree module from the sklearn library, which we had not imported earlier. Then we are setting the size of the figure by passing in the width and the height to the fig size parameter in the matplotlib library's figure function, and then by making use of the tree module here that we have just imported in this cell, we are calling in the plot tree function, and to this function we are passing in the object of the decision tree classifier that we initialized here for training. That is, this is our trained model, and here we are just passing the name of the features by accessing the names of the features that is stored in our x variable, and here we are passing in the class names, that is the unique values of the species column of the iris data frame. And then here fill true represents the color should be present in these boxes, as you can see in here, and we are then setting the font size, and the name is self-explanatory. And here we are passing in the title for the plot, that is decision tree for iris classification, and then we are displaying this tree. So now let us try to understand how a decision tree algorithm works. So a decision tree is a tree-like model, as you can see in here, where each internal node represents a feature, and each branch represents a decision rule and each leaf node represents an outcome. Now, the leaf nodes are these nodes which are not extending anywhere further, and these are the branch nodes that are extending further. You can see the arrows coming out from them. Okay, and the first node is called the root node, that is this node. The tree is constructed by recursively splitting the data set based on the most significant feature at each node. This process continues until a stopping criterion is met, such as maximum depth or a minimum number of samples per leaf. So either you can set the stopping criterion by comparing the sample numbers in each of the leaf, or you can choose the depth of the decision tree. Depth means the number of times it is being splitted. That is, if you will count the depth of this tree, then it will be 1, 2, 3, 4, 5. So minimum depth for this tree is 5, and this is the default value in decision tree algorithm for a stopping criterion. So decision trees are powerful because they can handle both categorical and numerical data, and they are interpretable, making them useful for understanding the decision making process. Now, I have already told you that when we were encoding the target variable, that it was not actually necessary to encode the target variable in this case, because decision tree can handle both numerical and categorical data. But still, for the sake of learning, we learn to implement that as well. So here you can see this is the root node. And here the petal length centimeter column is being evaluated. And this is the Gini index that represents the pureness of a node. And the less the value, the purer the node is. So it should be 0 for a node to be completely having data relevant to only one class. That we'll see later in this diagram. Next, here is the number of samples that are present currently. So since this is the beginning of the tree and this is the root node, all the samples are available at this point, that is 120. Okay, that was basically a train set, and the values are 40 for Iris setosa, 41 for versicolor and 39 for virginica. So this is the breakdown of the values. Now here the question that the model is asking is whether the petal length centimeter is less than minus 0.744 or not. And based on the result of this evaluation, this root node is being splitted into two nodes. Okay, these are the branch nodes, and here you can see that one of the resultant node is actually a leaf node, that is, it is not extending anywhere else, and it stops here because it is pure. You can see that the Gini index here is 0, and later on in the diagram as well, wherever there is a Gini index, the node are not branching off, that is, they are the pure nodes, and that is why they are called the leaf nodes. So here in the first step, you can see that there are 40 samples, and these values are 40 for Iris setosa and the other values are 0, as we can see in here. The class to which these samples belong to is Iris setosa. So here Iris setosa has been completely identified way earlier in the algorithm, and you can see that later on the only difference that the decision tree is trying to establish is between the versicolor and virginica, and we already know why this is happening, because there was a lot of overlapping in between the values of Iris virginica and Iris versicolor. And here the petal length centimeter column is being used to make such decisions, because in the data exploratory section we have already determined the usefulness of the petal measurements of the flower in distinguishing between the three classes. We could see in the graphs earlier that Iris setosa was completely different from the Iris versicolor and Iris virginica, and it was forming a different cluster, and there was no overlapping between the petal values, and that is being reflected here in the decision as well. That is, in the first branch we got a leaf branch, and that belongs to the iris setosa because that is completely different, right? And later on in the tree, the decisions are being made to separate iris virginica from versicolor because there was a lot of overlapping between these two values, but still it was less as compared to the sepal length and sepal width. In that case, the overlapping was much more. So again here petal length centimeter is being evaluated whether it is less than 0.564 or not, and here the Gini impurity is half. Okay, and the samples are 80 because out of 120, 40 samples are here in the iris setosa, and so we are left with 80. And now for these 80 we are trying to distinguish whether they belong to iris versicolor or iris virginica. And out of these 80, 37 were being classified as iris versicolor and 43 were identified as iris virginica. So just like this, the tree keeps branching off until it reaches pure nodes, that is the leaf nodes. Okay. So this is how the decision tree algorithm works. It keeps making the decisions. Here you can see these are the decision making nodes which are being branched off later on into leaf nodes. So to summarize, decision trees are powerful algorithms for classification tasks like iris flower classification, and we saw that the result was 100% in this case, but the data was small as well. So please don't be misguided by it. It's not going to be always the case when you will get such accurate results. They work by recursively splitting the dataset into subsets based on feature conditions. You could see that we have discussed a few conditions of petal length here, and based on its results, the tree keeps recursively splitting to create a tree-like structure. So that's a wrap for this project. If you have made so far in this project, then congratulations. You have learned how to train a classification algorithm, and to be particular, a decision tree algorithm for that matter. And not only this, but throughout this course, we learn to import necessary libraries. We learn to get familiar with the data, to load the data, to explore the data, to transform the data under feature engineering section, and then we learn to train and evaluate the model as well. And also we understood the workings of the decision tree algorithm and to plot it as well. We hope that you were able to gain some fundamental skills in classification. We hope that you were able to gain some fundamental skills in implementing classification, and we wish that you will use your learnings to further explore the realm of machine learning and classification. Thank you.